Start the class, sir.
Right. Good afternoon, students. Welcome to our physics class. Right, and we are discussing waves concept and competitive point of view discussing. Right. So the other day we discussed some important points regarding the competitive, that is meat and concept point of view. Now we will discuss some more synopsis to the rest of topics. That is, the foremost is intensity of wave, right? So here, first of all, we should understand what is this intensity, right? So the wave intensity is defined as the average amount of energy flowing in a medium per unit time normal to the unit area of the cross section. See this, of course, this definition is a little bit difficult to understand. But the thing is, I'll give just one example that, for example, in the room, in the dark room, if you lit one candle over there, right? So that candle spreads the lighting all over the room. But from the center, for example, the candle is at the center. So from the center to the corner, of the room, the intensity of that light will not be the same, right? So the source gives energy, right, all over the room, distributing all over the room, right? So the intensity is spreading. Means that intensity at far distance is small and near that source will be the more. But here, how much energy is dissipating, how much energy is flowing from the source? That is nothing but intensity with respect to time we are calculating, and with respect to area of cross section we are calculating. It's a three-dimensional picture. So the wave intensity is defined as the average amount of energy flowing in a medium per unit time normal to the unit area of cross section. Normal to the, okay, to the unit area of cross section. So as area increases, the intensity also changes. So expression for that is this: I is equal to, so this is, there are two formulae. One is in terms of frequency, another one is in terms of angular frequency. So I is equal to half omega square a square rho v, and another expression is I is equal to 2 pi square f square a square rho v. Observe this, a square rho v is common. Only thing is just rewritten this omega in terms of 2 pi f. Okay, so 2 pi f is 2 pi n of frequency, right? So here a is amplitude, f is the frequency, v is the wave velocity, and density of the medium is indicated with the rho here, right? So all these are involved in this expression. See that what intensity. So as intensity, see, that wave has some velocity, okay, that traveling in a particular medium. So density is the matter, medium is also matter, and amplitude means for intensity, amplitude, there is a relation. Okay, there is a relation. So we'll solve one problem on this. Okay, so, and one more thing is, in case of a point source of power, so whenever this intensity is there, the power comes out there. Okay, so yeah, so if the more power is there, the more intense. So here, in case of point source of power, okay, so at a distance r from the source, the intensity is given by the same expression in terms of power is here. So I is equal to P by 4 pi r square. See, P for particular power, okay, and 4 pi is constant, and this P by 4 pi is constant, and I is purely depends on the R here. See, R is the distance. See, that we know. So from the candle, I told you, from the candle, if you move away, okay, then intensity decreases. So both are inversely proportional. If R is more, intensity will be decreases, right? And see one more here. The energy associated with the unit volume of the medium is defined as the energy density. Yes. So actually the wave is a invisible quantity. So this physically we cannot feel it. Okay, so the energy associated with the unit volume of a medium is defined as energy density. So how much energy is there in that medium from the source which is coming per unit volume if you want to calculate. Then energy density. Actual density that it's a mass per unit volume like that. So but here it is a energy density, that the energy per unit volume. So energy is the intensity. Energy is nothing but how intense the light is, nothing but how energetic the wave is. So an intensity by velocity. Intensity by velocity. So this what this expression, see, intensity by velocity with respect to frequency is given here. So whole by v is equal to, so this much. Okay. So this is about the intensity of the wave, and the transverse wave along a stretched string. The transverse wave along a stretched string. Now here, see, in a stretched string, I hope we discussed this concept in the morning, so that when a string is stretched, then meanwhile at any point, if you pluck the the string, then release, then the transverse waves will travel along the length of the string. We have done a theoretical concept in the morning, right? So, and now we'll see the related formula to this. So, velocity of transverse wave along the stretched string. Okay, so in that stretched string, once you pluck and release, then what happens? It start oscillating and the wave will be formed, and that wave will move with a certain velocity is this here. So V is equal to under root T by mu. So T is tension of the string. See, based on the tension only, the number of oscillations and all will come to the picture. See, if you're more, because the stretching more here. If they stretch it, then the string undergoes tension here. And mu is the linear density or mass per unit length. So how long, how length the wire is also to be considered. Means what the linear density means, how much mass is present per unit length is also is very important. So that's what, see, mu velocity, I will say the relation is inversely proportional, right? If the density is more, the velocity will be small. The lean is there, the velocity will be more, and the thick will be there, then the velocity will be small. So the same thing. So density is equal to, okay, mass linear density to mass per unit length, and mass is already we know. So just now we discussed that what density is equal to mass per unit length. Yeah. So density is equal to mass per unit length, and if you want to calculate from that, mass is equal to area into volume. Yeah, area into density, right? So A volume A into L, area into length, volume, okay, and D here, and by length, right? Totally, so AD you are getting, that is area into this much. So pi r square D. So this is one of the equations related to the velocity here. So especially for the transverse wave, okay, in the stretched string. Now moving to this one, where R is the radius of the ring, sorry, string, and D is the density of the material of the wire. I'm repeating. So in this expression, R is what? Radius of the string, and D is the density of the material of the wire. So here the formula will become V is equal to T by, so in the place of mu, you can write pi R square D or A. Okay, so this is another form of equation. See, as per the problem, see in the problem, what information is given. So accordingly, we should use the formula. And here is another situation when the tension in the string arises due to a loaded mass. Okay, when to the same string, if the mass is loaded, then the string undergoes tension, right? So that tension is in the form of mg here. Tension is nothing but force. Okay, So as load is added over there, see here T is equal to mg. As F is equal to mg, we have the formula now. F is equal to mg, F is equal to ma. As mass is loaded over here, mg is acceleration due to gravity. So whenever the mass is there, gravity will come. So due to this parameter, the string undergoes some tension, that is F. So F is equal to ma formula. So in the place of T, we can write mg. So this is another situation. This is another case. Okay, so here we discussed the two situations here. That is when the mass is loaded to this. Okay, the area is considered, area of that string is considered, and simply mass per unit length is considered, linear density. So these are the three situations. And now moving to very important concept from this chapter as per competitive point of view. So Doppler effect. Okay, so today in the morning we discussed here. We just will go for this here. That the apparent change in the frequency. Just let me tell you clearly what is happening in the Doppler effect, so that if you are comfortable with the concept, then we can solve the problem. So the apparent change in the frequency, apparent change in the frequency. In the morning I told you, apparent means it is appears that it is a changing, but originally the frequency of that siren or a horn will be same only, but as per the observer, this is changing. So change in frequency of source and observer due to relative motion. Relative motion. This is very, very, very important. See, as long as the source and the observer both are at the rest, there is no change in the frequency. Okay, only when they are under motion, either coming closer or moving away. Okay, either of them, either one of them is the rest or motion. So like that, with respect to each other, if they are under motion, that is relative motion, then comes the Doppler effect. So the apparent change in the frequency of the source and the observer due to relative motion between them is called Doppler. And here is a small example. Okay, here is a small example that if the source follows source follows observer, as shown in the above figure, then the apparent frequency will be. See, in the morning, just as per IP, we discussed one case only. That is, in that case, what is that? Observer is the rest and the source is moving away. Only that case we discussed. And here so many cases are there. So one of them is if the source follows observer, means both are moving. Source follows observer. So who is moving forward now? Observer is moving forward. Back of that, the source is also moving. Then apparent frequency will be, is there any change in frequency? See, this is the formula. This is the formula that net frequency or n dash is equal to n into v minus v naught by v minus vs. Means v means original frequency and observer at what sorry, it's a velocities. Okay, in terms of velocities. Okay, so sound wave velocity and velocity of an observer and velocity of a source. Right, and here one more case we deal here, that formula for apparent frequency in different cases. Source moving towards the source, yeah, moving towards, and observer is rest. We I hope we discussed in the morning this. So f1 means f dash is equal to b by b minus bs into f. Okay, right. And here is another case, the source moving away from the stationary observer. The source is moving away. Okay, I hope both the things we discussed in the morning. So both are, see, in both the cases, observer is a rester, right? Stationary observer. Observer is the rest, and source is here moving towards, and here it is moving away. And here, observer moving towards a stationary source. Observer moving towards a stationary source. Yeah. So for this is an expression, right? Observer moving towards a stationary source. See, no need to derive for all the equation. So situationally, yeah. So just we'll go through all these formulae situationally. And observer moving away from the stationary source. So remember all these formulae, and we're going to solve one or two examples from these formulae. And here the source is moving towards a receding observer. Okay, source is moving towards a receding observer. At this case, this is the formula that f dash is equal to v minus v naught by v minus vs into f. And the next case is observer moving towards a receding source. Source is moving, the previous the source is moving, now the observer is moving towards. See, observe these signs here. Formulae looking same. Only thing is directions are very important. And now the relative velocity between the source and the observer is always taken along the line of sight of the source by the observer. This is very important. The relative velocity between the source and the observer is always taken along line of sight of the source by the observer. Line of sight means, for example, there is a wall and observer is other side of the wall, and source is this side of the wall. But the person means the source you cannot see, but you can hear the sound, no? Right? Even though the manually, physically, you can't see the source, but you can hear the sound. So here it is always along the sight of the source by the observer. So in which direction the source is, that is important. For example, the observer observing the source from the left side, what is the use if the source is coming from right side? So there is no use. So always it should be, means they should maintain some angle over here. So related to that is here, when the observer is at rest and the source is moving as shown in the below figure, then look at this. Okay, the source is here and the velocity of source is in this direction. This is called line of sight. This is called line of sight. And here is an observer. Observer is at rest. Observer is rest. And the source is moving like this. The source is moving like this. The source is somewhere and is moving like this. It's making some angle with this observer sight theta here. So this velocity component we are taking here, that is Vs cos theta. So this is called line of sight. This is called line of sight. Even though the source is moving away, but the component we are taking, the observer, yeah, he can listen the sound, even though the source is moving in this direction, but it is making angle. So that component we are taking here. So that is what is a line of sight. Okay. Next is the phenomena involved in beats is superposition. See, here is a beats component here. So a phenomena involved in beats is superposition of waves. In the morning we discussed, superposition means what? When the two waves are superimposed at a particular point at a particular time is called superposition. And this is the formula that we derived the expression in the morning, of course. So beat frequency is equal to, okay, the number of maxima heard per second. That is equal to number of minima heard per second. That is equal to number of beats per second. That is what? Beat frequency. Number of beats heard per second. That is change in frequency. F1 difference F2. So F1 and F2 are the frequencies of parent sounds. So originally the sources are releasing some sound with nearly equal frequencies. And the difference of that means if both are superimposed, then what happens? The resultant will be waxing and waning. That is maxima and minima. And here comes if N1 and N2 are the frequencies of the two sound waves combined to produce beats, then the combined beat has a frequency like this. Combined beat has a frequency. Okay, right? So combined wave has a frequency, this one, F1 plus F2 by 2. And the beat period, right? That already we discussed in the morning. So it is a frequency is nothing but what? Reciprocal, time period is nothing but what? Reciprocal of the frequency. So beat period is equal to 1 by F1 minus F2. And the time interval between the two consecutive maxima or minima. Maxima or minima. Okay, so the beat period is equal to reciprocal of frequency. And now is the time interval between the maxima and the next maxima. Very important. See, as per the competitives we are discussing here. Okay, so the time interval between the maxima and the next maxima is 1 by 2 times of F1 minus F2. Okay, so these are the very key points, some points to remember while solving the problems. Now we'll try to solve some examples here. Right, so we are going to solve some problems. We try to understand the problem very clearly, then only we can see the problem may be very typical. Answer is very easy. If once you catch the logic, maybe just within one or two steps only you can get the answer, right? So only thing is the understanding and approach is important. And here the problem, when a train is approaching a stationary observer, the frequency of its whistle appears as 120 hertz, while when it has passed the observer, frequency appears to be 60 hertz. Then the original frequency of the whistle is. I hope you understood this. Okay, the two situations are given. The two situations, one is approaching, another one is past. Okay, while the train is approaching the stationary observer, the observer heard the sound increasing frequency, that is 120, means because comparing with this. So now when it is past the observer, while it is moving away from the observer, the frequency appears as a 60 hertz. Then what would be the original frequency of the whistle is asking. Okay, I hope you understood the problem. Now here is the answer. The two situations were there. One is approaching, another one is moving away. One is approaching, another one is moving away. So one is approaching here. V1 is equal to V by V minus Vs into frequencies move here. So here also mu2 is equal to V by V plus Vs into mu. So here the ratio means divide these two equations. Then how much frequencies are given? Mu1 and mu2. Right? Mu1 is given, that is approach by separation, means moving away. Then 120 by 60 is equal to V plus Vs by V minus Vs. Just we are calculating ratio here. So this gets cancels there. Then simplify this, then how much you are getting here? V plus Vs is equal to, multiplied with the 2 on both sides, the 2V minus 2Vs. Okay, it will be cancelling 2 parts. Right. So 2V and here V, and minus 2Vs and here Vs. So how much you are getting? So this plus Vs will go, this will take this Vs here, this side. So it will be plus. So 3Vs is equal to, we are taking this side to V minus V, it will be V. Right? So 3Vs is equal to V. What they're asking, what is the original frequency they're asking, right? And now here 120 is equal to 120 is equal to, see, we got the velocity of source. We got the velocity of source. Actually, in this bracketed term, we don't know any values here. Velocity of source. The plane is moving with what velocity? We don't know. So 120 is equal to, only the frequency is given. So frequency is equal to V by V minus. Now we got V by 3. Okay, V is equal to, so Vs is equal to V by 3. We substitute here. So here V by, so V minus V by 3 is 2 by 3V. Okay, and simplify all these things, then we are getting, how much is the answer here? Okay, what is the answer here? 80 heads we are getting. Is it okay? Any mistakes are there? Nothing, no? Right. Right. 120 into 2 by 3. Yes, this answer. So right. So you are getting so 80 heads you are getting. So this is the frequency of the train. That is original, so not train, frequency of the whistle of the train. Okay. So what we have done, the problem just has given only frequencies are given. Only frequencies are given, right? 1 second. One second. Right. So here is, I will go for the next problem here. The difference between the apparent frequency of source of sound as perceived by an observer during its approach and recession is 2% of the natural frequency of the source. So the velocity of source is, what you understood? The difference between the apparent frequency of the source of the sound as perceived by an observer during its approach and recession. Okay, while it is coming closer and moving away, the percentage of apparent frequency they observed as 2%. Okay, to the natural frequency. So there is the original frequency, but the observer observed the change in frequency. Observer observed the change in frequency, that is while coming closer and moving away, the percentage of change he observed 2%. Then what will be the velocity of source they are asking? And in the problem, velocity of sound in the air already given, that is 340 meters per second. And here is the answer, and here is that given difference. One is coming closer, another one is moving away. Okay, approach and okay, moving away. Then one is V by V minus Vs into mu, and V by V plus Vs into mu. That is equal to, what is the ratio of what? Initial one. So 2 by 100 ratio, that is 2%, 2 by 100 to the initial. Okay, so to simplifying this, so doing LCM and all, okay, cross multiplication, LCM and all, so taking out mu here, right? 2Vs, do this simplification, okay, right? And 2Vs by V square minus Vs square into V is remained here. Okay, and anyway, the ratio is 2 by 100. So now observe this, Vs square is very much less than v square, because the velocity of see velocity v is what velocity of sound, that is 340 meters per second, and here velocity of source velocity of a source is moving with a certain velocity. Okay, so that definitely will be smaller than this original velocity. So that's why v square values will be neglected, means once it is squared the values will be very small, so it will be neglected. So the remaining thing is 2vs into v by v square is equal to this much, and this v gets cancelled, and 2vs by v, that is equal to here 2 also gets cancelled. Then finally you are getting vs is equal to v is multiplied this side, that is what we already given in the problem, that 340 by 100. So that's what 3.4 meters per second. Okay, so what is the key point in this? Just try to understand the problem. Just the observer observed difference. Okay, while it is coming closer and moving away, observed the difference. 2% of the initial is given in the problem. That's it. So that difference and observer, so 2%, both are equated and simplified, and only thing is as given only the original velocity of the sound is given. So your answer is 3.4 meters per second. And now we'll see the one more problem. A whistle revolves in a circle with angular speed. A whistle revolves in a circle with angular speed 20 radians per second. Okay, angular speed, right? Angular velocity. Okay, right. Using a string of length 50 centimeters. Okay, so using a string of length from where to where they are not given, but the length of the string is given, that is 50 centimeters, revolving around the circle. Right, if for the frequency of the sound from the whistle is 385 hertz, then what is the minimum frequency heard by an observer which is far away from the center? Okay, so whistle revolves in a circle with an angular speed of 20 radians per second using the string of length 50 centimeters, and the frequency of the sound from the whistle is this much, 385 hertz, and the minimum frequency heard by the observer. So observer is very far from the center of that circle. Okay, and given the velocity of sound is given 340 meters, and what is asking? Minimum frequency heard by the observer. Okay, heard by the observer. Okay, so here is the solution, right? Apparent frequency heard by the observer is the formula, because observer is very far and the source is moving around. So while it is see, moving around means what? Continuously the observer or the source is moving. So formula is n dash is equal to n into v by v plus vs, velocity of source. See here, v and vs are the velocity of sound and the source respectively, and n is the actual frequency, original frequency. Now we know this velocity is equal to r omega. Velocity is equal to r omega. So velocity is equal to, okay, distance or radius of the circle from the center, that is the distance, and omega is the angular velocity is given over there. So velocity is equal to what's the value is given? 20 radians per second. Angular speed is given 20 radians per second, and what is this is what's that? Radius of the circle. Radius of the circle is given here 50 centimeters. Yeah, 50 centimeters, right? So radius of the circle, then it will be centimeters given, so we are converting that into meters, right? So it will be 0.5. Yes or no? So from the using the string of length, so that is from the center to the edge, 50 centimeters is there. Okay, so then it will be 0.5 meters and 20 heads, no, radians per second. So multiplying this, we're getting 10 meters per second, that is the velocity. So why we are doing this? Velocity of this thing. Okay, velocity of this value, that is velocity of source we are observing here. Velocity of source we are calculating here, right? So v is equal to already given 340 meters per second, and n is also given 385. Okay, n is given 385. What is n? Is the uh, whistle sound, whistle frequency. Okay, right? That is 385 hertz. So original velocity, velocity of sound is given. So finally, n dash is equal to, what's the formula? 385 into 340 by 340 plus 10 using this expression. So n dash is equal to 385 into 340 by, okay, by 340 by 340 plus 10. So totally we are getting, after simplifying this, we are getting 374, right? Is your answer. 374. The option is correct. Okay, so only the logic is condition, situation, if you observe well, the situation if you observe well. Okay, right. So here is one more problem. Two identical piano wires kept under the same tension. Piano wires are given, so tension, the wires will be under tension T, and having a fundamental frequency of 600 hertz. The fractional increase in the tension of one of the wires, which will lead to occurrence of the 6 beats per second when both the wires oscillate together would be. So here two wires are there, two identical piano wires are there, kept under the same tension, so force is same. Then fundamental frequency of them is 600 hertz, and the fractional increase in the tension of the one of the wires, which will lead the occurrence of 6 beats per second. Then both the wires oscillate together would be, okay, so one of them is making 6 beats per second, and when both are oscillating, then what will be the fractional, okay, fractional change is asking. Yes or no? So when both the wires oscillate together, right? So here what they're asking, look at this, fractional. So we're getting fraction here. Okay, so fractional increase the tension, one of the wires, which will lead to occurrence of the 6 beats per second, right? So one is leads with the 6 beats, and comparing the other thing, then what will be the ratio, the change in this? So we have the formula, velocity is equal to 1 by 2 L under root T by mu. We discussed it here, this expression, that is T is the tension of the wire, and mu is the what density, linear density of the wire. Okay, L is the length of the wire. Okay, and what they're asking here, the change in frequency, right? Change in frequency is nothing but reciprocal, right? So 1 by T, right, is equal to delta T by T. So change in time, right? So sorry, change in tension. So change in tension by T. So change in tension is how much here? That is 6 by 100. Okay, 6 by 6 beats per second. 6 beats per second. So 2 into, how many wires are there? 2 wires are there. So here you are getting what? 2 into 6 by 600 is equal to 0.02 is the ratio. And we'll go for next problem. But yeah, so I'm concluding with this. Note it down this as a assignment. Okay, so this is one of the problems. Actually I need to discuss this, but the time is not permitting, so note it down, and of course the answer is here only. Okay, so I'm explaining, I have given the answer for this, and solve the remaining problems given here as a assignment. Okay, I'm giving 4 problems here. Okay, all are old problems come across in JEE mains, NEET, in MZ somewhere. Okay, so here 4 problems are displaying on the screen. So note it down and try to solve them. Okay, right. So here we'll conclude with try to understand the problems first. Yeah, let us explain this problem. Here the two sources of sound placed close to each other are emitting a progressive wave given by. The two sources are placed close to each other. Okay, already two sources are very close, are emitting progressive waves like this. Okay, one is this and the another one is this. Y1 is given, Y2 is given. Now an observer located near these two sources of sound will be, means the two sources are coming like this and the observer is observing both the sources simultaneously. Means both the waves are reaching the observer. Then uh, observer located near these two sources of sound will hear like this. Is options are given like this: 4 beats per second. The intensity ratio is like this, and between the waxing and waning, and 8 beats per second, and waxing and waning is at this ratio. And similarly, 8 beats per second with intensity ratio is 81 to 1, and 4 beats per second with intensity ratio of 81 to 1. So like this, the options are given. So now the solution is here. What are the common things already we have done in the last class, means yesterday's class, using these equations and the common terms you take out. And here for y1 is this and y2 is this, and identify the terms. What is 2 pi here? What is omega? Whatever, all the values are given here. Omega is given. The omega is converted to 2 pi like this, and from that you can calculate the frequency and amplitude, because amplitude is given for the first wave here. A is a sine omega t, right? So A, and similarly calculate for the second wave. Okay, second wave. So amplitude is 5, and the number of beats heard per second is nothing but difference of frequencies. And here maximum minimum, already there I told you the amplitude related. Okay, the beats concept we discussed in the morning. So substituting all the values, amplitude 4 is came here, 5 is there, and substitute the values and we're getting the ratios here. And the number of beats heard per second is difference here. So here 304 and 300 is there, and the difference is 4. That is what number of beats, and the ratio is like this. And these are what this is what the problem. And here the take this as an assignment. Okay, right? So we'll conclude with this. Okay, we'll continue the next class. Thank you very much. All the best.